Hi everyone, we're going to do a very quick lesson 3 on balancing chemical equations. What I'm going to tell you here is that most of the important information that I have for you in this video is about why we have to do this. In terms of actually doing it, I've got a couple of examples for you, but it's really a skill that you get good at just by practicing. So hopefully you'll understand at the end of this video why we balance equations. Hopefully that'll sink in really clearly, but the actual doing it, as I said, it takes practice. Just learning about it, listening to me talk about it is not going to actually teach you that concept. So this lesson is going to be pretty short, and I'm going to give you a lot of practice to do. Okay, learning goals. So we're going to have to state the law of conservation of mass. Can you say what the law of conservation of mass is? Because it turns out that that's pretty crucial to understanding why we balance equations. So we're going to connect the law of conservation of mass with balancing equations, and then most of your time is going to be spent on the third learning goal, where you're actually balancing chemical equations. Okay, so the law of conservation of mass says that matter cannot be created or destroyed in a chemical reaction. So in other words, you can think of it even as mass, but also as matter. So if you have 10 grams of a substance of reactants before you begin the reaction, you're going to have 10 grams after you finish the reaction. And if you have, say, 20 hydrogen atoms before the reaction, you're going to have 20 hydrogen atoms after the reaction. So you're not creating or destroying atoms or matter. Whatever you have at the beginning, you have at the end, just in a different form. Okay, so remember that's because, as we said in the last lesson, when you have a chemical reaction, all you're doing is breaking or forming ionic and covalent bonds. So when you do that, you're just changing the way that the electrons are shared or transferred between atoms. The atoms themselves are still there, right? So if a hydrogen atom shares its electrons differently, or if a lithium atom gives up its electrons, it's still a lithium atom, right? Or if it's, as we said with the hydrogen example, it's still a hydrogen atom. If a chlorine atom gains an electron, it's still chlorine. So the identity and number of atoms doesn't change. Okay, so if we look at this reaction where you have CH4 plus O2 to give CO2 and H2O, you'll notice that we have a 2 in front of the O2 and a 2 in front of the H2O. This is balancing the equation. So in the previous lesson, I was writing it without any coefficients, without any numbers in front of any atoms, and just leaving the numbers after the atom. If you put numbers here, you're balancing the equation. So what this 2 means is you have 2 oxygen O2 molecules, right? You have 2 of them rather than just 1. And that's important because if you have just 1, there's no way this reaction can happen. Look what happens if you have just 1 of those. So imagine that this part isn't here. Well, then you're going to have 4 hydrogen atoms, 1, 2, 3, 4, the white here, 1 carbon atom, the black, and then if this wasn't here, you would have 2 red. And you have to make 2 red here, and if you didn't have 2 of these, you would have a 3rd red. So 2 red has to make 3 red. Well, that's not possible according to the law of conservation of mass, right? Because you would then be creating an extra oxygen atom, and that doesn't happen. You don't create or destroy new atoms. So again, if you imagine that this is not here and this is not here, then you'd have 2 reds becoming 3 reds. So in order to make this make sense, you have to say, okay, well, I'm going to have 2 of those and 2 of those. So now we have 1, 2, 3, 4 reds on this side and 1, 2, 3, 4 reds on that side. So when you're putting coefficients in front, what you're doing is making sure that however many atoms you have on the left side, you have on the right side and of the same type. So you can see we have 4 oxygen, 4 red, 4 hydrogen, 1, 2, 3, 4 hydrogen, and 1 carbon and 1 carbon. So this equation is possible. So the only way you can get CH4 and O2 to react to give you CO2 and H2O is if you have a 1 to 2 to 1 to 2 ratio. And we write these in lowest terms. So you could, if you know your math, you could put a 2 there, a 4 there, a 2 there, and a 4 there, and it would still work. But we write these in lowest terms. So if you notice that all your coefficients can be divided by like 2 or something like that, please do that so that you've written this in lowest terms. So that's why we balance equations, so that the number of atoms on the left and the type is the same as the number of atoms on the right and the type. So again, 1 carbon, 4 oxygen, 4 hydrogen. Okay, so if we consider this following reaction, Na plus Cl to give you NaCl, this is already balanced, right? Cl doesn't normally exist like this, but if we just imagine it does, 1 sodium and 1 chlorine can give you sodium chloride, because you have one sodium here, one sodium there, one chlorine there, one chlorine there. We are not violating the law of conservation of mass. So some equations are already balanced. But others need to be balanced. And the one thing to note where there's often a mistake made is you can add a 2 in front. You can change your coefficients. So you could put a 2 in front of the CaCl2 or put a 3 there. This number, though, you cannot change. The subscripts, the small numbers, you cannot change those numbers. And the reason you can't do that is because this number is not telling you how many CaCl2s you have. It's telling you how many Cls there are per calcium chloride. And that's different because if you change that, you're changing the identity of the substance. Think about it this way. Water, H2O, right? Water is H2O. We're all familiar with water. There's another substance called hydrogen peroxide, which is H2O2. So if I write this in here, I'll write it in here actually. So if we have water, which is H2O, and we have hydrogen peroxide, H2O2. These are very different chemicals. This one you need to drink to live, right? It's really important. It's a very stable substance, doesn't really react very much. This substance is very reactive. You might be familiar with it in that we use it to treat cuts on your fingers or wherever. It's used to bleach hair. It's a very reactive chemical, which is why it's dangerous to cells, right? We mentioned that as well. So if you take the 1 that's after the O and you change it to a 2, you are actually changing the chemical. And so that's not the same reaction anymore, because you're saying that you're producing, like this reaction, if I put a 2 there, I would be saying that hydrogen and oxygen produce hydrogen peroxide rather than saying they produce water. That's changing the actual chemical that I'm producing. Whereas if I balance this equation by putting a 2 there and a 2 there, all I'm saying is I have 2 water instead of 1, but it's still water, right? It's the same chemical. And I have 2 oxygen instead of 1, but it's the same chemical. So don't change the subscripts, because if you do that, that's like adding a different ingredient in your cake. It's like changing your ingredients. Whereas putting a 2 here, you're keeping the same ingredients, you're just adding more of them. Okay? So you can't change their subscripts, just change your coefficients. So if I'm balancing this first equation, if we look back, I've got a couple of examples for you. These are already balanced here. I'm going to pretend they're not. There's no easy systematic way to balance equations that I can tell you, like always do this and it will work. So this is why practice is just really important. You'll notice certain patterns and you'll just get good at kind of counting up atoms very quickly in your head. So it's really important that you practice. But in this equation here, you'll notice it's not balanced because I have 2 oxygens on the left side and only 1 oxygen on the right. So I'm going to correct that by putting a 2 there. This 2 means I have 2 waters. So each water has 2 hydrogens. So I have 2 times 2. I have 4 hydrogens, and I have 2 oxygens now over here. So I have my 2 oxygens, but now the problem is I have 4 hydrogens on the right-hand side. I only have 2 hydrogens there. So I'm going to put a 2 there, and that will balance this equation. So I have 4 hydrogens, 2 oxygens, and 2 H2Os gives you 2 oxygens on that side as well. Next one, we have a combustion reaction. So in a combustion reaction, there is a usual approach that you can take that will work. So I'll just tell you what I would normally do. So do the CO2 and the H2O first, do the oxygen last. Because when you change oxygen, you're only changing one element. There's just an O there. If you change these, you're changing more than one. So it's a little easier to just change one at the end because you have a little bit more flexibility. You can kind of make this as many oxygens as you want. Whereas if I change this, I'm changing the oxygens, but I'm also changing the carbons. So 1 carbon on the left, 1 carbon on the right. I'm not going to put anything here. Carbons are already balanced. 4 hydrogens on the left, 2 hydrogens on the right. That's not balanced. I'll need a 2 there to give me 4 hydrogens, so I'll do that. But that now gives me how many oxygens? I've got 2 H2Os, so that's 2 oxygens, and 2 oxygens from my CO2, so that adds together, and you have a total of 4 oxygens on this side. So I need 4 oxygens on the left. I'll put a 2 there. And keep in mind that when you're playing around with this, right, you can add numbers and then delete them later. If I thought that I was supposed to put a 2 there, but it didn't work, I could delete it and put something else. So play with it until you get the right answer. All right, last example, double displacement reactions. So in this type of reaction, often it's useful to treat the polyatomic as one thing. although that won't always work. Sometimes you'll have to count up the nitrogens and the oxygens and everything in there, and we'll do that as well. But in this type of equation, it's often useful to think of them as one thing. So for example, you can see that on the left side here, I have 2 PO4s. On the right side, I just have 1 PO4. So I'm going to put a 2 there so that I have 2 PO4s. Okay, so if you think about it this way, I have 2 phosphoruses now on this side, and I have 2 phosphoruses on that side. Let's see what else we have happening here. So I have 3 calciums on that side. I have only 1 calcium there, so I'm going to put a 3 there. Again, if you do this, you're going to sometimes get the wrong answer, but you can play with it and get the right answer out of it. So now what do I got? I've got 3 times, I have 2 NO3s in each one of these chemicals. CaNO3-2, I have 2 NO3s in each of them. But there are 3 of those structures as a whole. So that's a 3 times 2. I have 6 NO3s, so I'm going to put a 6 there. And let's see if this is, maybe if we're lucky, it's already balanced. Let's see. So we got 3 calciums on this side, 3 calciums on that side. We've got 2 phosphoruses on this side, because remember this 2 means you have 2 PO4s. So that's 2 phosphoruses, 1 from each PO4. And this means you have 2 Na3PO4s. So if you've got 2 of this whole thing, you're going to have 2 PO4s. Or if you like, you have 2 phosphoruses, if we're counting those. So we have the same number of calciums on the left and right. We have the same number of phosphoruses. We have 2, and we have, each of these has 3 sodiums, and I have 2 of them. So that's 6 sodiums on the right, 6 sodiums on the left. So good so far. 6 nitrogens on the left, because I have 6 NaNO3s. Here I have NO3s. I have 2 of them every time I have one of these chemicals, but I have 3 of them, 3 of those chemicals. So I have 3 of a chemical that has 2 nitrogens. So 3 of 2, 3 times 2, I have 6 nitrogens. So 6 and 6, that works out. Oxygens is tricky because I have them between two different compounds on both sides. Here I have 2 PO4s. Each PO4 has 4 oxygens. I have 2, so that's 8. And then 6 times 3, I have 18 plus 8. So I have 26 oxygens on the left-hand side. That's a lot, but that happens sometimes. On this side, I have 2 NO3s in each of those. So I have 6 oxygens in each CaNO3-2, but I have 3 of those. So again, 3 times 6 is going to give me 18. And I have a PO4 here in this compound, and I have 2 of those, so that's going to give you 8. So again, 18 plus 8 gives you 26. So I have 26 oxygens on both sides. This actually is balanced. Okay, so again, it takes a bit of practice. Please practice. Send me questions if you have them. Attend my office hours, and hopefully you should be fine. All right, that's it. Have a good one.